Yep. All right. Thank you everyone for coming. I'm going to give this talk with these sunglasses on because I thought they were really cool. I brought them downstairs, so I can't see you as well as I should. My name's Dr. Jen Gupta. I'm an astronomer. I work at the University of Portsmouth down on the south coast in a department called the Institute of Cosmology and Gravitation. And I'm going to talk to you a little bit about the invisible universe. But before we get on to the invisible universe, we need to start with the visible universe. So what do we see if we go out and look up into the night sky, look up into space? We've had a hand up there. What do you see?
Stars and the air.
Yeah, so we see stars through the air that's above our heads, that's right. And you can hopefully just about make out on this image that we've got a few stars. This is the kind of picture that you'll get from a town or city. This was taken from Cardiff, and you can see the 3 stars here making up Orion's belt. Betelgeuse, one of the most famous stars, up there on one of his shoulders, his feet over here. But you don't see that many stars when you go out at night in a town or a city because of light pollution. So there's this glow along the horizon there. There's all the lights that humans make, all those house lights, all those street lights. All of that drowns out the light from the fainter stars. So to really see the sky, what we need to do is go somewhere dark. You go out into the countryside and you see a view a little bit more like this. And you can see so many stars that actually it can be a bit confusing, because you look up and you can't immediately pick out these recognizable patterns, these constellations like Orion that I showed you in that last picture. Orion's still in this picture, but it even takes me a second to pick it out. Here's Orion's belt now, 1, 2, 3, and there's Betelgeuse up there. So in a way, this is the invisible universe. This is the part of the universe that we can't see from our towns and cities. All of these faint stars along here are invisible to us when we have a lot of light pollution. But that'll be a bit of a cop-out if I was just going to talk to you about light pollution for 20 minutes. So what else do we do? Well, for as long as people have been people, really, we've looked up at the stars. I think astronomy is the oldest science. We've looked up, we've tried to work out what's going on up there with these distant stars. We've looked up and we've seen the moon at certain times of the month and at certain times of the year. When the planets are in the right places compared to us, you can see some of the planets. These are Jupiter and Venus in this photograph. And people, as I said, have used their eyes for thousands of years, but it wasn't until just over 400 years ago when Galileo and other astronomers took the optics, the lenses that had been developed hundreds of years before in the East, took that knowledge of optics, put lenses together on a tube and made telescopes to point up at the night sky. These are a couple of Galileo's telescopes in a museum. And this revolutionized our understanding of the universe. When Galileo pointed his telescope up at Jupiter, he would have seen something a little bit like this photograph. Obviously, this isn't a photograph taken by Galileo, but these are his drawings up here. So what you see if you look at Jupiter with a small telescope is the big disk, that's the planet Jupiter, the big circle there. But you also see what look like little stars on either side. That's what he noticed. And what Galileo noticed as well was that the position of these stars changed from night to night. So as you can see here, on one night he had 1 over here on the left and 2 on the right. Another night he had 2 on the right, on the left and 2 on the right. And so he realized that these must be something, these stars, what he thought were stars, that we actually know now are moons. These were objects that were going around Jupiter. So they were in orbit around Jupiter. And this backed up this new idea that was emerging that the Earth wasn't the center of everything. That the Earth and the planets, in fact, go around the sun. The moon goes around the Earth, but the other planets can have things going around them as well. And we built better and better telescopes since then. These are pictures you can take with amateur telescopes, showing you some color on Jupiter, and then really starting to get into the detail of what you can see on its surface. Until you get to the best optical telescope that we have, the Hubble Space Telescope, showing you incredible amounts of detail, not only on Jupiter, but also on the moons that we can see in these images. And telescopes have allowed us to do amazing things. They have revealed, in a way again, the invisible universe to us. They've shown us planets, Uranus and Neptune, that aren't visible to our eyes. These are just too far away, too faint for us to see. And the Hubble Space Telescope has given us some of the most stunning images of star formation regions and galaxies out there in our universe. And I think that astronomy, astrophysics, cosmology, whatever this science is that you want to call it, the science that I do, that my colleagues do in Portsmouth, it's one of the most accessible and inaccessible sciences at the same time. It's accessible because all of you can be astronomers. Anyone can go out at night, providing it's clear and not cloudy, like it is probably going to be tonight. As long as you can go out and you can see the stars, you can be an astronomer. You can look up at the stars, look to see any planets, shooting stars. You can go out observing night after night, and you can try to work out what's going on up there. You don't need a telescope. Of course, it helps you to have a telescope, but just with your eyes, you can do astronomy. So it's hugely accessible, but it's also completely inaccessible because we can't ever go there. We can't go to these galaxies that are crashing together and actually get bits of them and test them and see if our theories are actually correct. Everything that we do when we study the universe is we rely on the light we can collect. We rely on what we can see, and in some cases what we can't see. So we have to go beyond just zooming in on what our eyes would see, and we have to manipulate light in other ways. And one thing we do is we take advantage of the fact that what we see as white light is actually made up of all the colours of the rainbow. So many of you will be familiar, hopefully, with these kind of images, that when you shine white light through a glass prism, the light gets split out into its components and you get this spread out of a rainbow. Hopefully most of you will have seen a rainbow. The exact same thing happens with our rainbows in the sky. The white light goes through a raindrop and is split up into its components. But not all lights give off this rainbow. So this is what you see if you put white light through a prism. If you take a gas like hydrogen and you make it glow, and you put the light that hydrogen gives off through a prism, you'd see something like this. So when hydrogen gas, the most abundant element in the universe, the first element in our periodic table, when you make that gas shine by putting energy into it and pass that light through a prism, you would get this pattern. So instead of seeing all the colours of the rainbow, you see a couple of sort of blue purples, a turquoise and a red. And this is called the spectrum of that element. And every single element in the periodic table, some of these are more familiar than others. Helium, this one here, is what happens if you take that gas that you put in your balloons that makes them float up. Take that gas, put energy through it, make it glow, you would get this pattern of lines. If you have sodium in your street lights, your orange street lights, you pass that light through a prism, you get this pattern. Oxygen that we breathe, neon, making those neon signs. And the spectrum of the element is like its fingerprint. It's unique to that element. So now we can identify our elements in our stars and our galaxies. We can identify what stars and galaxies are made of just by looking at their light and manipulating it. One of the first people to do this was this woman, Margaret Huggins. And what she and her husband did was basically devote their lives to astronomy. So their house was an observatory. They were based in London. They had a telescope on the roof. And they took their telescope, they took the light through a prism and onto photographic plates, and they took photos of the spectra of stars. So this is one from one of their publications in 1877. And so you can see, this is obviously not in colour, but you can see those lines where the bright colours are, and you can identify the elements. This is the sun's, and this is another star's. Today we don't use photographic plates. What we do is we use computers to turn them into graphs. So this is the Sloan telescope. It's a 2.5 metre telescope in New Mexico. And we turn them into graphs. So this is essentially colour along the bottom, and every time there's a spike, that's where there'd be a line of bright colour. And so we can work out what's going on in our stars and our galaxies, because different types of stars and galaxies show different elements. But still, that's just using visible light. That's taking the light that we still can see and manipulating it. But what we see as this rainbow, what we see as visible light, is only a small part of what makes up the electromagnetic spectrum. So when we see rainbows like this, it doesn't end there. There's light that's more red than red, we just don't see it. And there's light that's more violet than violet, and we don't see it. And so if we go to the red part, beyond the red we get infrared light, and then over to microwaves and radio. On the other end, on the violet part, light that's more violet than violet is ultraviolet, and then that goes ultraviolet, X-rays, and gamma rays. And we can build telescopes to detect each type of light and then we truly are seeing the invisible universe. So I'm going to take you through this spectrum now, and I'm going to show you objects at each wavelength. But before I do that, I thought I'd show you some examples, everyday examples of where you might come across this type of thing at home. Because obviously, these terms might not be as familiar to you. You might not be familiar with thinking about them as light, but you will hopefully be familiar with some of these examples. So radio waves we use for communication. We use to send out our TV and our radio signals. Your mobile phones use radio waves. Microwave light is used in your microwave oven. What's actually happening in your oven is your microwaves, the microwave light, is exciting, is giving energy to the water molecules in your food, and that's what makes it heat up. Infrared light is used for thermal imaging. Have you ever seen any cop shows when they're looking for the bad people from the helicopters at night, and they're using thermal imaging? What they're actually doing is picking up the infrared light that humans give off. Ultraviolet is the UV light that comes from the sun, the harmful rays that you put your sun cream on to avoid. They give you a tan that some people go and expose themselves to ultraviolet in sunbeds to get that same effect. X-rays are used in medical imaging. And I couldn't think of an everyday use of gamma rays, but if any of you are familiar with the Marvel universe, then the Hulk becomes the Hulk in those stories because Bruce Banner is exposed to a lot of gamma rays. Don't think that would happen. Please don't go and try that. You'd probably just die. Okay, so here's our electromagnetic spectrum, and as I said, I'm going to go through each one, and I'm just going to show you a snapshot of the kind of things that we as astronomers pick up with those different types of light. And of course, we find a lot of different objects in all of these different types of light, but I just picked one example for each. So starting off with radio. Radio, I've picked a galaxy. This rather boring looking blob there is what's called an elliptical galaxy. This is a collection of over 100,000 million stars, all held together by gravity into basically a rugby ball shape, so it just looks like a blob of stars to us. And this is an image that an amateur astronomer took. Now, M87 is really hard to see in the kind of telescopes you can go out and buy, but it is possible. If you want that challenge of trying to find it, here's a really not helpful screenshot from Stellarium. So it's there. This is the constellation of Leo, so look for the backwards question mark of the lion's head and then down to his tail, and that sort of points you down to M87. If we take a picture of M87 with the Hubble Space Telescope, so zooming in on that optical light, that visible light, then we already see it's a little bit weird. So this is 1/4 of that galaxy, and we see something coming out from the center. Most elliptical galaxies don't have that, so we already know it's a little bit weird. But it's not until we go to the radio image that we really see what this galaxy is all about. So this is a radio image. It's obviously false color because we don't see those radio waves. So the red is where the most is coming from, and then yellow, green, and then finally blue is the background. And it's at a different angle, but this is that same thing coming out from the center that was coming out in this bit. And what's happening here is that M87 is what we call an active galaxy. So this is the middle of the galaxy, and in the middle of every galaxy is a supermassive black hole. So a black hole that's maybe 1 million or 1 billion times the mass of our sun. And in most galaxies it's not really doing anything, but in galaxies like M87 it's a monster. So it's actively eating up all the material around it, and that's swirling round and falling in to the black hole in the center. And then somehow these jets form. I say somehow because we don't really know how they form, and I spent 4 years doing my PhD trying to figure out more about the physics of these jets. But what we think they are is magnetic fields coming out like this, and then you've got charged particles like electrons, the negative part of the atom. And when you get charged particles with a magnetic field, they spiral round. And so there's electrons spiraling around the magnetic fields here, and as they do that, they give off radio waves. That's what's happening here. That image was taken with the Very Large Array. So this is a radio telescope in New Mexico. Looks like lots of radio telescopes. There's lots of dishes here. But it's a technique called interferometry. We can't build really giant radio telescopes because you just can't do that engineering. You can't build them much bigger than 100 meters across. And really, to get the same resolution, the same amount of detail as the Hubble Space Telescope, what we want at radio is a telescope that's the size of England. So instead of us all standing here in these buildings and living here, we would just have to have one giant dish. So we can't do that, I don't think. So instead what we do is we build smaller dishes, and you see they're all pointing up into the same part of the sky. And it's as if we had a radio telescope that stretched from there to there, that was that big. Okay, I've probably talked about radio astronomy too much because I'm a radio astronomer. I better move on. So next we go to microwave, which is essentially the same as radio to astronomers, but there's one very important thing that we pick up in the microwave, and that's the entire sky. So this is an all-sky picture in the optical again. So this is what we would see if you could see the entire sky. So imagine that you go everywhere on the Earth and you take a photo looking directly up, and then you stitch all those together. You've essentially got photos stitched together that cover the inside of a globe surrounding the Earth. So we just unfolded that to make this two-dimensional picture. And all of this is our galaxy. So this is us looking through our Milky Way galaxy, and all of this is dust, all that dark stuff. If we look at this with a microwave telescope, this is what we see. So here, white is the most amount of microwaves, going to blue, and then red and yellow. So again, we see lots of stuff coming along this line. It's microwaves coming from our galaxy. But what we actually want to do in the microwave is get rid of all of this, because what we're interested in are these little speckles at the bottom and at the top. So once you subtract that, once you take away all the microwave emission from our galaxy and from all the other galaxies out there, this is what you're left with, this speckly picture. And what this is showing you is the oldest light in the universe. This is light that was emitted 380,000 years after the Big Bang, so nearly 13.5 billion years ago. It's been travelling out ever since. It's called the cosmic microwave background radiation. And this is basically a temperature map. So this light you can think of as having a temperature that's 3 degrees above absolute zero. It's really cold. What the red parts here are showing you are areas where that light is 1/1,000,000th of a degree hotter. And the blue areas are showing you parts that are 1/1,000,000th of a degree colder. So you've got tiny, tiny temperature changes, temperature fluctuations in the cosmic microwave background radiation. And that tells us more about the Big Bang, about how the universe came to be. And it tells us about the large-scale structure of the universe today. Why galaxies are where they are can be traced back to this picture. This picture was taken with the Planck satellite. This is a spacecraft. This is the artist's impression of it. It has to be in space because it has to be really cold to pick this up. So what you can see actually is the sun's there and the Earth is here and Planck is behind it. So it's going 4 times further away from the Earth than the moon, and it's going round behind the Earth so it can stay really cold. Next is infrared. It's our thermal imaging. For infrared, I want to take you back to Orion. So here's the 3 stars of Orion's belt. And hanging down from his belt, down here, is his sword. And if you look at that from a dark sight, you will notice that one of the stars in his sword doesn't look like a star at all. It looks a little bit fuzzy. That's because it's not a star. With an amateur telescope, you'll see something like this, and you'll realize that this is a nebula. This is a cloud of dust and gas. And the Orion Nebula is actually a star formation region. So this is where stars are being born. Here's the Hubble Space Telescope picture of it. And you can see all this dark stuff is all dust and gas. And that's where the stars are being born inside. You can see 4 bright stars here, but you can't really see much else. What we want to do is be able to see those stars forming, see those young stars. And so we go to the infrared. And the infrared shows us this. You suddenly see about 300 stars in this picture, I think. These ones really shine out. But these ones all around are cool brown dwarf stars and stars that are just forming. Both of those pictures were taken with the Hubble Space Telescope. This is a real photograph, the only photograph of a space telescope I'm going to show you. Hubble is known for being an optical telescope, for zooming in on what we see, but it's also got infrared and actually ultraviolet cameras on it. Okay, ultraviolet then. Ultraviolet, I've picked this object. This fuzzy little object is called M31, or the Andromeda Galaxy. If you want to find it, it's over here. So this is Cassiopeia, one of the most recognizable constellations, and you can use these 3 stars to point you to Andromeda. But if you're looking for this with your eyes, you're going to be disappointed, because you have to be somewhere really dark. Look there out the corner of your eye, you might see the smudge of light that doesn't look that impressive. But with our professional telescopes, it looks much better. And you realize that M31 is this spiral galaxy, looking like we think the Milky Way looks like. That faint smudge of light is a collection of 100,000 million stars. So what you see with the spiral galaxy is you can see that there's different colours. Here in the centre is what's called the bulge of the galaxy that looks kind of yellow. And then coming out of the spiral arms, they look quite dark here because there's all that dust where the stars are forming. We go to ultraviolet and it looks very different. Now you can hardly see the centre, but this arm, this spiral structure is really obvious. And this is showing us all the youngest stars that are forming. When young stars form, when they form, they're very hot. I mean, all stars are hot, but the youngest ones are the hottest. And they glow so brightly that they glow violet and ultraviolet. And that's what we pick up here. That was taken with a space telescope called SWIFT, which is here, an artist's impression. That's actually an X-ray and an ultraviolet telescope, which leads us on to X-ray. So for X-ray, I picked one of the most recognisable objects from the Hubble Space Telescope. You probably don't recognise it from this because it's another fuzzy blob. There's a lot of fuzzy blobs in astronomy. This is the Crab Nebula. It's over there, sort of above Orion's belt. Up there, there's Betelgeuse. But hopefully some of you will recognise this picture because this is on coffee table books all over the world. And the Crab Nebula is a supernova remnant. So this is what's left over when a star much bigger than the sun has come to the end of its life and died in an explosion. All of this stuff here that we see in the Hubble picture is all the gas in the outer parts of the star that's been flung out in that explosion. But the core of the star collapses down in a supernova explosion. And if the star is big enough, it becomes a black hole. If it's slightly less big, it becomes what's called a neutron star, made up of the neutral part of the atom. And that's what's happened to this one. We can't see that in this picture, but if we point an X-ray telescope at it, we can see that, which is absolutely incredible. Here is our neutron star. And our neutron star here in the Crab Nebula is actually also what we call a pulsar. It's giving out two beams of radio waves and X-rays. Can you see this beam coming out there? There's another one coming out there. And it's like a cosmic lighthouse. It's got these two beams and it's spinning round. So just like a lighthouse will sweep past you, these beams of radio and X-rays will sweep past you. And we can pick them up. And we time them, and they go so accurately that they're actually more accurate than an atomic clock. That was taken with the Chandra telescope, another X-ray telescope in space. Obviously, these ones have to be in space because X-rays don't get through our atmosphere. It's a good thing, otherwise we'd be fried here on Earth. And finally, gamma ray. Now, gamma ray is a little bit different. Gamma ray astronomy is a bit younger than all the other types of astronomy because you have to build your gamma ray telescopes a little bit differently. Gamma rays are so energetic that you can't focus them. All of those telescopes work essentially as mirrors. So you remember the radio dish? It was like that. The radio waves come down, are reflected off the dish and up to a point where they're picked up. Gamma rays can't do that, so we have to be a little bit different with them. So for gamma ray, again, all I can show you is the entire sky because that's as far as we've got with taking gamma ray images. So here's our optical picture. And here's our gamma ray picture. So again, yellow is the strongest gamma rays, then red, then light blue, then dark blue, black in the background. And again, we see lots of gamma rays coming from the Milky Way, but it's not that the Milky Way gives off a lot of gamma rays, we're just inside it. So all those sources of gamma rays are much closer to us, so they seem stronger. What I'm really interested in is all the little dots that are outside of our galaxy, above and below that line, because nearly all of those are these active galaxies, like M87 that I showed you in the radio. And it seems that radio galaxies, like M87, are really bright at radio waves, but also really bright at gamma rays. So they dominate the two extremes of the spectrum. And that's really interesting. Why are they doing that? And that's something that we're still working on to try and figure that out. That was taken with a space telescope. This is Fermi. As I said, it works a little bit differently. So this box is your telescope. And it works like a detector at a particle accelerator. So what you've got here are layers of material. Your gamma ray comes in and it can turn into a particle and antiparticle. It's just something that can happen. And then they can sort of travel down until they hit a detector layer at the bottom. And then you work out, you measure the energy of those particles, you measure which direction they came from, and you kind of trace it backwards to figure out where your gamma rays came from. So that's our spectrum. If you like looking at the multi-wavelength sky, at the invisible sky, I would urge you to check out Chromoscope. It's a website some of my friends put together where you can scroll through the different wavelengths, the different images at different, so we're down to infrared now, and have a look at the sky. So that's chromascope.net. Or if you fancy getting involved with some of this science, then at Portsmouth we're involved with a thing called the Zooniverse, which is a citizen science platform, where we ask members of the public like you to help us with our research. So this project is called the Milky Way Project. Basically, this puts up infrared pictures of our galaxy up there, and they want you to pick out like bubbles. So there's a little bubble here, or star clusters and things like that. And that helps us to do our science, to work out more about the Milky Way. So that's at milkywayproject.org. Or Radio Galaxy Zoo is another one. This shows you an infrared picture. That's what the colour bit is in the background. And then these contour lines are your radio picture of the same part of the sky. And this asks you to match up whether the radio, the contours and the picture match up if there's radio emission and infrared emission at the same place, to help us find those radio galaxies like M87. So I will finish there. If you want to find out more about me or where I work, then there's all the details. But thank you very much, and I'm happy to take any questions.
Thank you, Jane. Has anyone got any questions for Jane?
Yeah, that new big, what's it called, dish in China.
The one in China, FAST.
What is that?
So FAST is a much bigger single dish than we've built before. So what they've done is they've taken a crater essentially, and they've made a dish into that. So it's 500 meters across. That's really looking at cosmology, I think. So what that's trying to pick up is neutral hydrogen in the universe, to try and map out what happened sort of after the Big Bang.
Really early.
Pardon?
Really early.
Yeah, so trying to look at radiation that's coming from really far back in time.
Is there anything that's obvious to you at the minute that could be more linked to signs of life, that's possibly closer to it than we've ever come?
I think we're going down the right lines. I think Mars is really interesting for looking for life in our solar system, and there's a couple of moons of like Jupiter and Saturn that could host life. Mars, Airbus Defence and Space are involved with a project called ExoMars, so that's a European mission to go to send a rover to Mars that will go, I think, next decade. And that's going to be the first one to look for signs of life. But when we say life on Mars, we mean like microscopic life. So it would be things like bacteria that you might find on Mars. And it might have died out a long time ago, so you find the fossils of it. But Mars is showing more and more signs, I think, of possibly having conditions in the past to host life, and even still today. So a year or two ago, some people announced that they've seen evidence for flowing water on Mars. So we know that there's ice. We know there's frozen water on Mars, but we weren't sure if there was any liquid water left anymore. So you see like the dried up riverbeds, equivalent to like the Grand Canyon on Mars. But we weren't sure if there was still liquid water anywhere. And what they saw was seasonal changes, basically. So streaks going down a dune that could be from water running down. So Mars, who knows? I think we're gonna get there. No aliens yet, but I mean, it is a serious field. So there are people doing astrobiology, which is looking looking for life on Mars and places like that. I've got friends who sort of study extreme life here on Earth and try to compare that to Mars. And then there's also SETI, which is a search for extraterrestrial intelligence, which is basically trying to tune into their TV signals using those big radio telescopes. So it's a two-pronged approach, and I reckon we'll get there. But don't.
What does Area 51 know already?
That I think I would say all of the alien sightings, all those conspiracy theories on Earth can be explained by humans. I would imagine Area 51 and things like that. My bet would be that it was military, super secret military aircraft and things that they were testing, and they wanted to keep it a secret, so they said it was aliens instead.
Any more questions?
Yeah, you mentioned the radio images were false colour.
Yeah.
Colour represented intensity.
hmm
So does that mean that they're only taking that single wavelength?
Yes. So most of them will be a single wavelength within that band. So that I can't remember which one that. I can't remember what specific wavelength this one was, but it's essentially looking at, as you said, one wavelength, which is basically one colour. So we can do the exact same thing in the visible. We can take just the blue light, and we can go even further than that. You remember the spectrum that I showed you? We can just take, say, the red line of hydrogen, and we can take an image just of that light that's coming from a galaxy. So that's the exact same thing here. I think this might be 6 centimetre wavelengths, but I'm not sure.
Can you do the analogue of visible photography in the radio stage?
Yeah, so you can take along at different wavelengths along within each waveband, or you can take a lot of the pictures that you see, astronomical images, will actually be like a radio image combined with a visible image combined with an X-ray. And so what they would do is, instead of having this as a false colour, you turn this into like a black and white intensity image and then give that a colour. Does that make sense? So you'd make all the radio emission blue, but it's just lighter or darker, brighter or dimmer, depending on how intense it is. And then you do the same for optical. You'd assign yellow or something, and then X-rays assign red, and you fit them all together. So even that Crab Nebula image, even this isn't, a lot of these optical images aren't what your eyes would see. So again, here, like one of these colours will be the oxygen light coming from, like one line of oxygen, and one of them will be nitrogen or something. They're not, if you could go there and see that, it wouldn't necessarily look like that. That makes sense. Cool.
Thank you,
All right.
Jen.
Thank you.
very
I'm going to
much.
be outside if anyone's got any questions they don't want to ask
Or
now.
if you've got any questions.
Cool.
Great, thanks. Staying with the staff space theme, we've got Sarah Elmore next with how to make a star on Earth. If you want to stick around for that, we'll try and get some more people in. We'll take 10 minutes. Shout it about.